Hi there, it's me again, Farizal. Continuing on our course BJTM 3063, Automation and Robotic. We are now in chapter number 5, which is the number systems and codes. The lecture outline for this chapter will be on the decimal system, binary system, negative numbers, octal system, hexadecimal system, BCD system, Gray code, and ASCII code. Let's start off with the decimal system. Actually, decimal system is a base 10. This is the usual numbers that we always use. The base of the number system determines the total number of different symbols or digits used by that particular system. The total number of symbols is the same as the base, and the symbol with the largest value is 1 less than the base, which is 10 unique numbers. The digit is from 0 to 9. So basically, the numbers that we use, usually you are being taught the numbers are base 10. The weighted value of each position can be expressed as the base 10 raised to the power of that particular position. So I will show you how to use this power of to the position, and then in the next slide. The position weight are 1, 10, 100, 1000, and etc. Let's look into this example. This is a number for the decimal, which is in base 10. The value is 1962, which is in decimal, base 10. So now, if you remember on the previous slide, this notes the weighted value of each position can be expressed as the base 10 raised to the power of that particular position. So, for example, this number 2 here, alright, the position, the power of the position is equals to 0. So it means that 2 multiplied by 10. 10 is the base 10. Position to the power of the position, which is 0. So 2 multiplied by 10 to the power of 0 is equals to 1, which will give us a value of 2. Next one, if we look into this 6, the position is number 1. Alright, so 6 is equivalent to 10, which is the base, to the power of the position, which is 1. Alright, is equivalent to 6 multiplied by 10 to the power of 1 is 10, will give us a value of 60. Next, we look into the second position here. The value is 9. Alright, 9 to the power of 10, which is the base. The position is 2. So 10 to the power of 2 is equivalent to 9 multiplied by 10 to the power of 2 is equals to 100. So 9 multiplied by 100 will give us a value of 900. As for the last digit, which is 1, the position is 3. Okay, so 1 multiplied by the base, which is 10, to the power of the position, which is 3. Alright, 10 to the power of 3 is equivalent to 1000. 1 and 1 here is 1. So you just 1 multiplied by 1000 is equivalent to 1000. If you look into the summation of this number from top to the bottom, when you add up everything, you will have a value of 1962 to the base of 10. So basically, this is how you use the base number with the position of the number to the power of the position to evaluate the the total value based on the base of the numbers. We will look further on this conversion in the next slide. Now, let's look into the binary system. Binary system basically is a base 2. If you remember in the previous slide, the decimal is in the base of 10. So for binary, the base is equals to base 2. In this case, for the binary system, only 2 digits are allowed, which is digits 0 or digit 1. So only these 2 digits are allowed in the binary system. Binary system is applied easily to the PLC, which is the timers and counters and computer system. We have learned about the PLC in the previous slide. The weighted value is 2, which is the base, raised to the power of the position. Each digit of a binary number is also known as a bit. We will look into the example of the binary system later on in this chapter. Now, let's look into an example of changing from binary base number to a decimal. Let's consider the value for the binary number is this one, which is 1 0 1 0 1 1 0 1 is a binary number, which is a base of 2. Now we need to change from base of 2 to base of 10. So what should we do? We need to know, first thing first, is the location of the digits or the numbers, alright, which is this one. This one is 0, and then 1 2 3 4 5 and further on, alright. And then doing the same thing like this one, if you remember, alright, what we will do is that we need to have 1, bring it down to 1, and then 2 to the power of the position is equals to 0 to the power of 0, because this is a base 2. We want to change to base 10. Alright, so what happened is that 1 multiplied by 2 to the power of 0, which is equals to 1. 2 to the power of 0 is always equals to 1. So 1 multiplied by 1 will give a value of 1. So continuing on the second digit, which is 0, the position for this 0 is 1. So you will get 0 multiplied by 2, which is the base, to the power of 1 is equals to 0 multiplied by 2, which gives us a value of 2. The next one, we have this 1 to the power of 2, with 1 multiplied by 2 to the power of 2, which is this one. The location of 1 here is equals to 2. Alright, so 1 multiplied by 2 to the power of 2 is equals to 1 multiplied by 4, because 2 to the power of 2 is equals to 4. So you will get a value of 4. Continuing on again, so this one is number 1 multiplied by 2 to the power of 3, which is the location. Right, to the power of 3 is equals to 1 multiplied by 2 to the power of 3 is 8. So you will have a value of 8. How about the fourth number 1? This digit, the location of this digit is equals to 0 multiplied by 2 to the power of 4. The location here, right? The location is 4, alright? So 0 multiplied by 2 to the power of 4 is equals to 0 multiplied by 16, which gives us a value of 0. How about the next one? We have this one here, 1 to the power of 2, 1 multiplied by 2 to the power of 5. You see this location 5 here, right, is equals to 1 multiplied by 32. 2 to the power of 5 is equals to 32, which gave us a value of 32. And so on until the end, which is this one. 1 to the power multiplied by 2 to the power of 7 in this case is equivalent to 1 multiplied by 128, which gave us a value of 128. So when we sum up from top to the bottom, what value that we got for the decimal is 173 to the base of 10. So you see, it's a bit different. In binary, you only have either 1 or 0, but in decimal, you have all the digits from 0 to 9. Right, so this is how you change from binary to decimal. Still talking about binary numbers. As being mentioned in the previous slide, binary numbers is the only language that being used by the PLC. So the PLC only understand either it is 1 or 0. The PLC processor memory consists of hundreds or thousands of locations, which refers to as a words. Alright, each word is capable of storing data in the form of binary, digits, or bits. Alright, basically the PLC processor memory are keeping all the preparing hundreds or thousands of locations which being referred to as a particular word for each of these locations. Alright, the number of bits that word can store depend on the type of the PLC system used. Most common is 8 bits, 16 bits, or 32 bits. Bits can also be grouped within a word into a byte. So when you combine bits, it will become a byte. At 8 bits, use a byte, and a group of 1 or more bytes is a word. Alright, so basically when you combine from bytes and you group it together, you will have a different name we call as a bytes, B-Y-T-E-S. 8 bits use a byte, okay, and a group of 1 or more bytes in a word. So this is how the binary system works. Still continue on the binary numbers. Alright, binary numbers is a bit within the word can be existed only in 2 states. Alright, either it is a logical 1 or on condition, or logical 0 for off position. So this figure down here illustrate a 16-bit word made up of two bytes. Alright, so where is the bytes? This is the upper byte, this is the lower byte. So there are 2 bytes. Alright, so each of the bytes represent 8 bits. 1, 2, 3, 4, 5, 6, 7, and 8. So each of these bytes being represented by 8 bits. So that's why I said in figure below, for the 16-bit word made up of 2 bytes, this upper byte and also the lower byte. Now let's look on how to convert the decimal to binary. This is an example on what is the procedure, what is the steps needed to change the decimal numbers, which is in base 10, to the binary number. So basically this is how we want to change number 47 to a binary number. It is the same like the previously we have discussed on how to change from binary to decimals. This is binary to decimals. Now we want to change from decimal to binary, the other way around. So how we want to do it? Alright, first thing first, you need to take the number, the decimal number, and then you need to divide by 2. Since we want to change from decimal to binary, binary is a base of 2. So you need to divide by 2. So you will have a value of 23 with a remainder of 1. Alright, and then continuing on for the number 23. Alright, you divide by 2 again. Alright, you will have a number of 11 with the remainder of 1. Alright, and then when you continue on, so from 11 divided by 2, you will have 5, remainder 1. Alright, and so on until the end value of 1, whereby 1 cannot be divided into 2. So the remainder for this one is 1. As you might have noticed, there is these acronyms of MSB and also LSB. What is the MSB and LSB? MSB stands for most significant bit, or MSB. As for the LSB, it stands for less significant bit. Alright, so LSB. Why do we need to know MSB and LSB? It's because when you want to arrange into from decimal to binary, you must know which number should come first. So for all of the system conversion from decimal to the binary, the most significant bit will always start first. So in this case, the most significant bit is 1, right, which is this one, followed by 0, followed by 1, 1, 1, 1. So it means that 47 is equivalent to 1, 0, 1, 1, 1, 1. So I hope you understand on how to change from decimal to binary. Another things that keep coming up from this topic is on the negative numbers, right? In binary system, okay, an extra digit or sign bit, an extra digit or sign bit is used to represent the positive and negative value of the MSC sign of the number. In sign bit position, which is 0, alright, indicates it is a positive. 1, however, indicates the negative. Alright, I will show you an example of in the next slide. So you see here, this is the negative numbers. Alright, this is the negative numbers table. As being told in the previous slide, 0 is being represented as a positive, right? 0 is a positive, and then 1 is a negative value. So you can see here, this 0, 1, 1, 1 represent the value of 7. Alright, binary of 0, 1, 1, 0 is a positive 6. 0, 1, 0, 1 represent the positive 5, and so on until here. Now, when 1 pop up, which is this one, this number 1 pop up, it means that the value is in a negative mode, decimal. The value is in negative. For example, 1, 0, 0, 1 in decimal is minus 1. 1, 0, 1, 0 in decimal, the value is minus 2, and so on until the end. For example, 1, 1, 1, 1 represent the value of negative 7. So this is the table for the negative numbers in binary. After the binary system, the next system that I will teach is that on the octal system. So this is the octal system. Octal system is to eliminate too many binary digits in PLC. If you remember, -7, the value for binary is 1, 1, 1, 1. How about -700 or -7000? What will happen to these particular binary numbers? So it will be a haywire. So that's why we introduce another thing which is being called as the octal system. Alright? Octal numbering system is a base 10. Right? Binary is base 2. Octal is base 8. Is often used in microprocessor, computer, and programmable control system or PLC. So we keep using this octal system in this kind of equipment. Three, two, one. Octal is used as a convenient means of handling large binary numbers as shown in the next table, not 5.3, as shown in the next table. One octal can be used to express 3 binary numbers. One octal can represent up to 3 binary. Okay, let's look into an example of this one in the next slide. Alright, so you see here, okay? So for binary, okay, the value for binary from binary to octal, if the value of binary is 0, 0, 0, definitely. In octal, it is also 0. 0, 0, 1 in octal is 1. 0, 1, 0 in octal is 2. So you see, 3 digits is being represented by 1 digit, right? In this case, we are using the octal system. So until the end, 1, 1, 1 represent the number of 7. Okay? Three, two, one. Now look. 3, 2, 1. Now let's look into an example of converting octal numbers to a decimal. So if, for example, you have this value of 462 to the base of 8, which is an octal number. Now you want to change into a decimal number. So what you should do is that you need to bring down these two. Okay, 2 multiplied by 8. Why 8? Because the base is 8. The base is 8 and you want to change to decimal. Okay, 8 to the power of 0 is equivalent to 2 multiplied 1, which gave us the value of 2. 6 multiplied by 8 to the power of 1 is equivalent to 6 multiplied by 8, which gave us a value of 48. And lastly, for 4, 4 multiplied by 8 to the power of 2, which is the base number, is equals to 4 multiplied by 64 is equivalent to 250. What we need to do is now is that to add up all these three to get a value, decimal value for this number. So basically 462, the decimal number 462 is 306 to the base of 10. 3, 2, 1. Now, let's look how to convert an octal to a binary. Remember, binary is either 1 or 0. Alright, so now we want to change an octal number, the value of octal number of 4, 6, 2 to the base of 8 into a binary number. So for this one, it's a bit easier, alright, because you know each of these value is being represented by a binary number from this table. Alright, for example, now 4, it is in binary is equivalent to 0. Right, so you see 4 is 0, and then we go for 6, which is 1, 1, 0. Alright, so this is one. So for 6, you want to change to binary, 1, 1, 0. 4 represent back to binary is 1, 0, 0. And lastly, for 2 is being represented by 0, 1, 0. Alright, for the value of 2. See here, 0, 1, 0 is is the binary number. It represents the value of 2 in the base of 8. The system is 16-base system with the value of A to F, okay, used to represent the numbers 10 to 15 for this A to F. We will look into the table for hexadecimal system in the next slide. So basically, this is the table starting from decimal, and then octal, hexadecimal, and also by binary. Okay, so for example, the value of 1 is equivalent to 1 in octal, is equivalent to 1 in hexadecimal, is equivalent to 1 in binary. So let's look into this example. For example, this number 10 here. Alright, the value for the octal the value of 10 in octal is equivalent to 1, 2. And the value for this number 10 in hexadecimal is A, which is alpha. Alright, so these 2 digits represented by this one digit. Alright, and as for the binary, it is 1, 0, 1, 0. Alright, let's look into another photo example. For example, this 15 here. Alright, the value of 15 in octal is equivalent to 17. The value of 15 in hexadecimal is being represented by F, and the value for 15 being represented by the value of 1, 1, 1, 1 in the binary system. As usual, we need to convert, in this case, convert hexadecimal to a decimal value. Alright, for example, we have an hexadecimal number which is 1B of Bravo 7, 1B7 base of 16. Now we need to change from hexa number to a binary. So in this case, 7 multiplied by 16 to the power of 0 is equivalent to 1, and then B, alright, is 11 actually, multiplied by 16 to the power of 1 is equivalent to 11 multiplied by 16, which will give us the value of 176. As the last number, which is 1 multiplied by 16 to the power of 2 is equivalent to 1 multiplied by 256, and the value is 256. So what we need to do is that we need to sum up all of this value from top to bottom, which give rise to a value of 430 to the base of 10. So this 1B7 is equivalent to 430 430 in base 10. Let's look into another system, which is what we another number system, which what we call as the BCD system. All right, the BCD system provides a convenient way of handling large numbers that need to be input to or output from a PLC. So it provides a means of converting the code readily handled by humans to a code readily handled by the equipment, which is the binary system. This is the table of change conversion from decimal to BCD to binary. For example, if we take into example of number 8 here, this number 8 in decimal it is 8, alright, which is base 10. When in BCD it became 1000. As for the binary, it is also the same, which is 1000. If we look into the example of number 12 here, the value for decimal is 12. The BCD value will be 0001, and then for 2 is equivalent to 0010. But for the binary system, it is being simplified for a value of 1100. This slide shows us on how to convert the decimal to BCD. For example, we have a value of 7863, which is in the base of 10, or this is a decimal number that we usually know. Alright, now we need to convert to BCD. So how to convert it is just by referring this binary to the respective values in the table, like here. So for example, 7 decimal is equivalent to 0111 in the BCD. So you see, 7 is equivalent to 0111. How about number 8? Number 8, the value for 8 in BCD is 1000, which is this one. See here, 8 is 1000. So continuing further with the value of 6, which being represented by 0110, and the value of 3 is being represented by 0011. So this is the BCD value from the decimal number. So if you notice, alright, each of this number is being represented by 4 bits, 4 bits for each decimal digit. These are the values that easily understood by the computer or by the machine. For us, we understand this number, which is in decimal, but for a machine, they only knows the value of either 0 or 1. We are almost at the end of the slide, but before that, I will show you on the how to change the value to base number using calculator. So in this case, we have two examples, two websites that shows us on how to change the value from decimal to the respective base number. Alright, the first website is from this one, and second one is from here. So for your information also, you can always try to explore on how to change the decimal number to a base number on your own personal scientific calculator at home. So let's look into the website. The first one is this one, how to change from decimals to binary or hexadecimal. This is an example of a website to change from basic decimal number to any of the binary, octal, or hexadecimal number. I give you an example. First thing first, we need to key in the decimal or octal or binary or whichever value that whichever base number that you want to input. For example, we say a decimal value of 876,543. Alright, this is in decimal. Okay, so the operation, just leave it blank first. Second number also leave it blank first. Alright, and then the value for 876,543 base 10 is equivalent to D delta 5 Foxtrot F base of 16 if you select a hex. So if in octal, it will be a value of 3257778, or if you want to change to binary, it will be this value 1101011011 and so on to the value of base 2. So if you want to put any operation, for example, 876,543, you want to add operation add with the second value, for example 321. Okay, so this 321 also in decimal, so you will have a value automatically 87643 plus 321 to the base of 10. The value for this summation will be this value. This is in the binary number, or you want to change to octal, this is the value 3260500 to the base of 8, or you want to change to decimal. Alright, if you want to change to decimal, it's 868764653 plus 321 is equivalent to 876864. So this is the value in decimal, or you want to change to hex. So you see the hex, the number is much small, the digits are smaller, which is D6140 to the base of 16. So just play around with this website, and as I told you, you can always also try to do the operation in your personal scientific calculator. You can also check this website if you would like to have a try on how to change different kind of value with their own respective base number. For numbers, we also can use a gray code. This is what being called as a gray code. I seldom use this gray code. It is not so popular. Alright, but at least you know that there is a number that being called as a gray code. The gray code is a special type of a binary coded that does not use position weighting. It is not suitable for counting circuit, but ideal for encoder circuit. In these absolute encoders are position transducers that use the gray code to determine the angular position. The speed of a transition of a gray code is faster than the BCD codes. So basically, this is the advantages of using a gray code on top of a BCD codes. I will not go further on this one. I think you can try to explore by yourself on how to understand what is the definition of a gray code. The last code for numbers is the ASCII code, or this ASCII codes stands for American Standard Code for Information Interchange. It is an alphanumeric code because it includes letters as well as numbers. So it have letters, letter, and also number. Letter is the alphabet A until Z, and then they also have a number. Alright, it is used to interface the PLC CPU with alphanumeric keyboards and printer. So this is the medium for us to interact between our own personal laptop and also to the PLC controller. Right, I also will not touch much on this ASCII code. It is interesting to understand about these numbers, but we must also learn on how these numbers are being changed, what kind of tools being used in order to change from one basic numbers to another different kind basic numbers. So this involve the encoding and decoding, alright, whereby the PLC uses a digital integrated circuit or IC chips for conversion from one number system or code to another. And encoder IC is used to convert from decimal to binary numbers. Decoder IC is used to convert back from binary to the decimal numbers as being requested. So we are using some kind of a chip, what we call it as the IC chips, alright, that use or being programmed or being designed to convert from one number to another number depending on to our requirement. I think that's about it from me. That's the last slide. So thank you very much for listening. I hope to see you again in the next video.